It is my pleasure and my honor to introduce you our friend, Professor Reshevsky. Only a short list of his positions. Head of the Department of Materials and Interfaces at the Weizmann Institute. Director of the Center of Nanoscale Science. Last time, if you agree, the member of the advisory board of the various clip functional nanomaterials. His field is physics, inorganic chemistry, material science as well. He focuses on the synthesis of new inorganic nanotubes and Fuller-like nanoparticles and investigation of their unique physical and chemical properties. If you want to know what happened, what is new in the world of nanoscience, you must read, and you must not read only, you must study the Reshevsky. H-index of Professor Reshevsky, 75. Number of citations, about 25,000. From 2011, Professor Pauling is a full member of Israel Academy of Science. He received many awards and medals from several academic organizations in Israel and from China, Taiwan, UK, India, Turkey, and so on. It's a list, a long list. I don't know. It's very difficult to okay. Reshev is a real friend of our institute, is known. For many years, he participated in various professional committees on academic promotion of our faculties, opening new academic directions. You know, part of you remember, with his active help, we opened the direction of material science in the faculty of engineering. It is a great honor for our materials center, for me, that recently we have begun scientific cooperation in the field of metals hardening by additives of nanoparticles with Professor Reshevsky. Reshevsky, thank you very much for your help.
Thank you very much.
Please take Professor Reshevsky.
Thank you very much.
It's a great pleasure to be here again. It's a great pleasure. I have a special commitment here because my daughter takes her PhD studies course here in Ariel University. So I'm very glad that I can be part of the family. Part of my family is here already. So, and I hope in the future there will be some graduates of my group that will join the staff here, which is something I'm thinking and considering, and I hope that I can help establish Ariel University as an independent and successful university in Israel. But after all, it's up to you. You have to produce this excellent papers and excellent work, which will be then recognized by all the academic institutions. So I will tell you a little bit, if the light can be dimmed a little bit, that will help a lot. Can we turn off the lights? So I'll give you an overview, very short perspective of nanotechnology from, and don't be afraid. Those that do not understand Hebrew, the slides will be mixed, but I will speak in English and I will clarify every point. So I'll try to give you some perspective on nanotechnology from my point of view, and especially focusing at the end of the second half of my talk on 2D materials, which is now a very hot topic in the nanoscience community. There was just yesterday I saw a paper in Nature on 2D materials. So it's a very, very hot topic, and I will come to that at the 50% the latest part of my talk, maybe even less. Let's see. So I'll start with these beautiful structures which have been synthesized in my lab, nanotubes of nano-octahedra and fullerenes of molybdenum disulfide, and are very useful industrially now, with a big industry developing around these products now. And I want to give you some perspective to nanotechnology in order to understand that nanotechnology is not a new field. It's an old field, in fact. And we have evidence that the Egyptians already have had some understanding of nanotechnology. Of course, they did not call it nanotechnology. They did not speak the language we are speaking together today, but they have understood some clues in nanotechnology which are hard to imagine. They didn't know what chemicals are. They didn't have any technique to look at or to study their materials, but yet they were very professional in performing some beautiful artwork using nanotechnology. And this is the first example. These are gold nanoparticles embedded in gold, in glass vessels. And perhaps I can start to say that perhaps the most important artifact in the British Museum is this one, the Lycurgus cup from the 4th century, where it describes a war between the Romans and the Lycurgus, the king of Lycurgus. And here is the king of Lycurgus, the defeated king of Lycurgus. And this artifact is a glass vessel coated with gold nanoparticles. And you see very nicely the plasmonic hue of these gold nanoparticles by having it, the reflection is green and the absorption is red. So the light that goes through the vessel or the beaker, glass beaker, is red. The light that is reflected from the beaker is green. And if you look deeply into this Lycurgus cup, you see nanoparticles of gold, which are demonstrated by this beautiful high-resolution TM, which we can do today. And you see that we can see atom by atom. And furthermore, we can do tomography. Perhaps it's one of my forthcoming slides. Will show you tomography of gold nanoparticles. So we can count the number of atoms in each such nanoparticles. And the important thing is to see that they mastered the chemistry and the material science of this Lycurgus cup to that extent that they could control to a certain extent the colors of this vessel. And you see that the coating here is the hue is a bit different from this, which is probably due to the difference in size of these nanoparticles. As you can see here, how the hue of gold nanoparticles is different in different sizes. And this is possibly the most beautiful demonstration of nanotechnology, because you know very well that bulk gold is yellow, like my ring here. But when you go to nanotechnology or nanomaterials, it becomes very different, and you see all the different kinds of hues and colors due to the quantum effects, quantum size effects of this plasmonic excitation. So this is the first artifact that we know of that represent nanotechnology from the old times. And this is a second one, representative one, from the Renaissance period of time. It's a Majorca dish found in Umbria from the Renaissance period, from the 16th century. And it shows beautifully different landscapes described by using different silver, copper, and gold nanoparticles to describe this whole scenery. And perhaps all the colors here are contributed by nanoparticles, which are so beautifully arranged. And the chemistry is not that complicated, but nevertheless the control is beautiful. And you see how this dish describes in great detail the scenery, and it's all made of nanoparticles. So this, one can say that two leading areas of life that led to the development of nanotechnology is art and war. And I won't bring you examples from the warfare, but I can just tell you that everybody knows that Salah ad-Din won the Crusaders in the Battle of Arsuf, or in the Battle of... The reason that they one of the reasons that they were able to win the Crusaders, because they had swords from Damascus steel, and this steel is very flexible and not breaking. And the reason that it doesn't break is because the grain boundaries are decorated by carbon nanoparticles, even carbon fullerenes and carbon nanotubes you can find there. So I won't go into that, but this is another example how war was how the nanotechnology benefited warfare. So these are two threads of different threads that really led to the development of nanotechnology in the old times. Let me go to the modern time. And certainly the modern time starts with the work of Michael Faraday. Michael Faraday, in the 19th century, the most renowned physicist, chemist in the 19th century, he started the Royal Institution in London, and here is one of the discourse that he's presenting, and he presents for the first time the gold emulsions which are made of gold emulsions which are made of gold nanoparticles. And if you go to the cellar, to the basement of the Royal Institution, you can see this solution still there. And the beauty of this thing is, first of all, for the first time he understood that he can control the gold nanoparticles. He actually reduced acidic solutions of gold with some tin or with some citric acid, I'm not sure, and he was able to get very precise sizes of the gold nanoparticles, and by that change the hue of the gold solutions or emulsions. And Michael Faraday is by all means the father of colloid chemistry and nanoscience as well. So this is the beautiful demonstration of his contributions, as well as all the other contributions that we know of, Faraday law and all these other things. And in the 20th century, Zsigmondy took the lead in the early 20th century, and Zsigmondy was the father of modern colloid chemistry, and he started to study colloids and synthesize them in great precision, and using surfactants. And I will come to that when I get to the quantum dots and description of quantum dots and their contribution. So this is a modern history of how nanotechnology has developed. Let me go to the more recent times, and I'm going a little bit historically. You'll see that I go in history back and forth, and I'll go even to the Greek times in the forthcoming slides. So here I show you the picture of Erwin Schrödinger, and we all know the Schrödinger equation. The Schrödinger equation is the equation by which we calculate the eigenstates, the energy levels of excited state, and we can describe the absorption and the properties, the optical properties and the electronic properties of nanoparticles. So Erwin Schrödinger, he was not the only one, by the way. Heisenberg did the same technology, or developed the same equation using matrix algebra, but Erwin Schrödinger did it using differential equations, and that helped a lot to familiarize this equation with the scientific world. But in order to calculate the eigenstates of the nanoparticles, we needed to use the Schrödinger equation for at least for nanoparticles which contain hundreds of atoms, and that was not possible during Schrödinger time. And for that, we had to wait for Walter Cohen, who passed away last year. Walter Cohen formulated the DFT, the theory, that allows us to calculate the properties of nanoparticles using, of course, computer simulation, computer calculations. And DFT is the theory by which we calculate the properties, the entire physical properties of nanoparticles, and we can even calculate more than that. But still, DFT, due to the size of our computers, is limited to about precise calculations of the Schrödinger equation using DFT is limited to about 1,000 atoms, maybe 2,000 atoms, and we cannot go beyond it. If we want to go beyond, we have to use more approximate theories. But nevertheless, these two gentlemen really made a major contribution to our ability to calculate and predict the properties of nanoparticles ahead of the synthesis. And in many ways, they contributed to the development of nanosciences in a very well and defined way. And of course, when describing nanotechnology, one cannot overlook the major contribution of Richard Feynman. Richard Feynman actually stated the important sentence that we all cite today. There is a plenty of room at the bottom, an invitation to enter a new field of physics. And this was done in 1959, and Richard Feynman, after receiving his Nobel Prize, was a real big advocate of nanotechnology. And he actually suggested that if we can build structures from individual atoms, we will be able to make features, or to make nanoparticles which can be precisely controlled, and their physical properties can be precisely controlled. And therefore we call, in many ways, Richard Feynman the prophet of nanotechnology. Let me go now into in this overview. So first I give you an overview, a general overview, to two or three important groundbreaking technologies that allowed us to practice daily nanoscience and nanotechnology. So the first one is scanning probe microscopy, microscope כוח אטומי or microscope מנהור אטומי, electron microscopy, microscopia electrolyte, and clean rooms and nanofabrication. I will skip this point because I'm not going to talk about clean rooms and nanofabrication. That will require much more time to differentiate. I will just say that there are two main approaches to nanotechnology. The bottom up, from taking a molecule or an atom at a time and building up nanostructure, which is mostly popular, but in academic level, and is penetrating gradually into the industrial world. And the more usual way that people practice nanotechnology are basically the top-down, the one that is practiced in Intel every day to make features which are as large as 10 nanometer. So you know that in Intel now, they will start soon the nanofabrication of 10 nanometer transistors with gate size of 10 nanometer, with 7 billion transistors on one chip. So this is the top-down approach, and I won't describe this in this talk for the lack of time. But there is of course, a whole science and technology on that part. And let me go directly to the two pioneers of scanning probe microscopy, Heini Rohrer and Gerhard Binning, who received the Nobel Prize for that discovery in 1986. What is a scanning tunneling or scanning microscope or atomic force microscope? It's a tip that goes on the surface, very close to the surface, and can fill atom by atom and see the reaction of each atom in different ways. So the scanning tunneling microscope measures the tunneling current. The tunneling current is direct result of quantum theory, direct results of the Schrödinger equation, that atoms or the electrons are not limited to the atoms. They can tunnel out and go to the tip And if you measure this tunneling current, you can describe geographically or topologically the structure of the surface. Then you can also do analysis and much more than that, and I will come to that in a minute. And I just want to mention Aaron Lewis from the Hebrew University, who invented the ENSOM, the near-field scanning optical microscopy, which is now quite regular or research tool in many laboratories, and is very, very useful, and his company Nanonics in Jerusalem that builds and sells these setups. I just want to give you one example of using scanning tunneling microscopy and atomic force. Basically, this is an atomic force microscope. They don't measure the tunneling current, they measure the forces. And with a precision, unprecedented precision, they can measure the structure of each molecule. And more than that, they can measure the product of chemical reactions. And you can see that this molecule, by synthesizing one molecule at a time, you can actually probe the products, the two different products, by scanning, by atomic force microscope. In this case, this is a paper that was published in Science in 2013. And at the same time, almost at the same time, there was another paper from a Chinese group that demonstrated beautifully hydrogen bond between naphthalene molecules, and you see these features which are considered to be hydrogen bonds between these molecules, and there is a great deal of discussion whether this is an artifact or what have been really observed. Until today, the game is not set, but nevertheless, the demonstration that you can measure reaction products, you can measure in such a high precision hydrogen bonds, chemical bonds, is unprecedented. And of course, the fact that you can combine it with precise calculations using the Schrödinger equation or using the DFT is an amazing testimony to the power of modern science and modern nanotechnology. Let me go to the second most important, and perhaps the most important, in my view, contribution to nanotechnology and to nanosciences. And this is the transmission electron microscope, or at the same time, scanning electron microscope. So the pioneer is Ernst Ruske, by all means, and Otto Scherzer. They are two German scientists. And Ernst Ruske was in Berlin, and Otto Scherzer was, I think, also in Berlin in the beginning and then moved away. Anyhow, Ernst Ruske in 1933 already built the first transmission electron microscope, and there is a beautiful history to that, how he argued with his brother. His brother was a virologist, and he said that he will be able to see, and the discussion between the two was that Ernst told his brother, I think Helmut, that he will be able to visualize his viruses in better precision than any optical microscope, and therefore he built this beautiful microscope. And this microscope, as you know, went a long way. The first commercial one was commercialized by Siemens, which were in Berlin after the war. They started even before the war, but they really commercialized it after the war. And then Otto Scherzer said that the limit of resolution of electron microscopes will be given by the chromatic, by the spherical aberration and the chromatic aberration. So the spherical aberration is the effect that the rays that come from the side of the lens are not focused at the same point that the rays that come parallaxial, close to the center. So the different focuses do not allow you to make a very precise focusing of the beam. And this is solved in optical microscopy by the Abbe configuration, where you have focusing and the spreading defocusing lens coupled together. But in electron microscopy, it was not possible until 15 years ago. And Otto Scherzer he calculated and he tried to build a corrector for spherical aberration, and he was not able to do that at that time. But then came Rose, Heider, Urban, and Andrei Krivanek and built the first CS-corrected or aberration-corrected microscope. And this is the picture of a strontium titanite. Not only you can see the strontium and the titanium, you can also see the atoms of oxygen, which are very light and have very small contrast. And you can construct the entire puzzle of the strontium or structure of strontium titanite using the Pico microscope, which is the highest resolution microscope in the world in Jülich, Germany. And I participated in the inauguration ceremony and gave a talk there in the Pico inauguration a few years back. And now they have added another element, the chromatic aberration corrector, which was again done by Heider and Rose. And recently, a month ago, I participated in the inauguration ceremony of the new microscope in Ulm, which has both spherical aberration and chromatic aberration, and it's an unbelievable microscope. You can image atoms at the 20 or 30 kilovolts resolution, and that is really unprecedented. And I won't go to that because it will take me too much time. But I just will mention that the Weizmann Institute, we are buying now a series of microscopes of this kind, actually two and a half microscopes of this kind, and few other microscopes in order to be able to catch up with the rest of the world. This is a demonstration of gold nanoparticles in different angles with atomic resolution obtained by tomography. So I'll go now that I finished the first part, I will go to the second part, which is the different nanomaterials technologies that change the world or are going to change the world. And I will start with soft materials, on which I will talk just very, very briefly. Then I'll go to quantum dots. Then I'll go to self-cleaning titanium nanoparticles. And then I'll go to 2D materials, starting with graphene, fullerenes from carbon, and then at the end of the talk on my work on inorganic fullerenes and inorganic nanotubes. So let me start with soft material, and this is a demonstration of the marvels of nanotechnology in the nature, using, in the case of different applications, how nature makes use of nanotechnology to benefit. So you have the Lotus self-cleaning structure of Lotus. Lotus is a leaf that does not collect dirt, because the dust is collected with the water droplet. It's so hydrophobic, it's a super hydrophobic, and therefore the water droplets collect the dirt and they roll out of the leaf very easily. And the structure of these leaves is demonstrated, is actually shown here. This is an artificial structure, but nevertheless it's very reminiscent of the structure of the lotus leaf. And you see that it has a unique property for super hydrophobic structure, which allows it to be able to get rid of water very easily, and dirt, of course. And this is another example of the same structure, water strider. The water strider has tip. The tip of his legs are made like that, and he can really go on the water without being drawn into the water. And the last example is the Gecko effect. The Gecko effect is the super hydrophilic case. It's a lizard that can suspend from the ceiling, and is glued so strongly to the ceiling because the structure, it has the same structure, but there is a glue in between the features, so that the interaction between the tip of his legs and the wall of the ceiling is so strong. And I will just show you the first application of soft matter nanotechnology, which was produced by Chezi Bernholz from the Hebrew University in his medicine called Doxil. It's a pharmaceutical prescription which is made of a medicine coated with phospholipids, which make a liposome coating the medicine nanoparticles of the medicine, and goes through the body and target the cancer cell, and it's used to patients suffering ovarian and breast cancers. So this is the first medicine, or the first example, large-scale example of using soft matter nanotechnology to the benefit of mankind. Let me go now to perhaps the most important part of my talk, or one of the highlights, is quantum dots. Quantum dots are the most beautiful example demonstrating the Schrödinger equation, the quantum size effect. So basically, it tells you that if the electron is confined to a smaller and smaller size nanoparticle, the energy, the difference between the energy bands will grow, and consequently, the material will start to absorb more to the UV across the entire visible spectrum. So you see different cadmium selenide based quantum dots, and this one is the largest one, and this one is the smallest one, and this beautiful demonstrate this is the absorption and luminescence of these nanoparticles, and you can see with spherical aberration corrected TM, you can see beautifully the structure of one single quantum dot, and you can calculate by Schrödinger equation, by DFT, the spectrum of this quantum dot, and you can superimpose it on the experimental one, and you can see that each quantum dot will give you the same, or almost the same, because the control is so good on the size distribution, plus minus 2% or 3%, that you can really control them all to give the same color. And this has an important technological ramification, which I'll show in the next slide. So you are now getting a mobile phone with two very recent technologies that have been materialized and came to fruition. On the one hand, you have, so this one is the first screen commercialized this year by LG of a quantum dot containing a television set containing a layer or coating of quantum dots, which allows you to get many fine hues and colors from this high resolution TV screen. I think it's 50 or 60 inches in size, or maybe even larger. And it's the first demonstration of a commercial quantum dot-based TV screen. And on the left, you see a comparison between two recent technologies, the quantum QLED cell phone and the OLED phone based cell phone. And the display here is made with organic light-emitting diodes, which were invented by Tian and by Richard Friend, and I will not go into that. But the beauty of this display is that it's made all from polymers. All from polymers. It's unimaginable, almost unimaginable. If you think of how did we go from 100 years ago when Staudinger synthesized the first polymers, and how we proceeded with synthesizing polymers until 20 years ago. They were only used for structural items. They were not used for electronic application. And here you see a beautiful optoelectronic device made of polymers. I won't have time to describe that. And on the left, you see a quantum dot. It's basically a layer of quantum dots, and in front there is the liquid crystal display, and so it's a combination of liquid crystal display and quantum dot layer film that allows you to get this beautiful hue. So you see a very important application coming into fruition now after so many years of research on quantum dots. If you think of Zygmundi, who started the colloid chemistry, and then to Sasha Efrosh in Russia, and Louis Bruce in Columbia University, and Paula Livisatos and Bawendi in UC Berkeley and in MIT that developed the first quantum dots-based light-emitting diodes. Okay, so here is the beautiful demonstration of how nanotechnology influences our daily life. Let me go now to the work on self-cleaning titanium dioxide nanoparticles. This is the work of mostly Akira Fujishima, not necessarily. By the way, many of these people, the people here in the pictures are friends of mine, those that are living people, and Akira is a particularly good friend of mine. And he developed this whole concept of self-cleaning titania nanoparticles, and the idea here is that you have coatings of titania not rutile, the other version of anatase titanium dioxide, which can be very easily oxidized, or by absorbing light can lead to OH radical, oxidize water to OH radicals, and these OH radicals oxidize the surface of the titanium dioxide so that dust cannot stick to the titanium dioxide. And if water comes by rain, by a rainfall, or in a surgery room where you have the plates of ceramic plates coated with titania. So you see how the titania anatase titania nanoparticles are powerful oxidants, and they can keep the surfaces very clean for a very long time, provided you wash it from time to time. So here's a few examples, a recent example that I collected of this self-cleaning titanium nanoparticles, and I won't go into that, but it's a commercial product and technology that after 40, 50 years has been went into nanotechnology, and there are now a number of companies that are manufacturing these ceramic plates for self-cleaning surfaces. So this is another example of self-cleaning surface. And now I go to the last part of my talk, 2D materials. So I have 20 minutes remaining time, or 15 minutes. I will go to 2D materials, which is my main field of interest and is a huge scientific and technological activity nowadays. And there is a long history to that. I'll go to that in a minute, but I will start with the highlight of the discovery of graphene. Graphene, as you know, was discovered or rediscovered by Gaiman and Voselov in Manchester. They both young guys that received the Nobel Prize in Physics in 2010, and I know them, of course, very well. And they actually, what they did things that people knew a long time ago, to exfoliate graphite with Scotch tape, layer by layer. But they had the imagination and the vision to see that when you exfoliate graphene one layer at a time, you get actually a material which has, in many aspects, relativistic behavior. The electrons do not obey the Schrödinger equation. In fact, they obey the Dirac equation, which tells you that the electrons are massless, and therefore their mobility is huge, and the conductivity is fantastic. And they have calculated a variety of physical constants, including the absorption coefficient of one layer of graphene, which is 2.8%, which is given by the superfine structure constant beta, and they demonstrated that basically it's a relativistic translation of relativity on a solid state material. And for that, of course, they were awarded the Nobel Prize, and not for the graphene itself, because the graphene itself was produced earlier, a few tens of years before. But this graphene has actually led the world of physics to change dramatically now. And if you go to most physics journals, you'll see a lot of papers on or publications dedicated to topological insulators and materials which demonstrate relativistic behavior instead of massless behavior instead of electrons with mass, like the one that we are used in the case of transport properties of usual bulk materials. Graphene has the property also that it is very, very robust material. So this is a beautiful sketch of an elephant standing on a pencil, a graphitic pencil, and the graphene layer can support the elephant. Of course, it's not a reality because there are always defects there, and eventually the elephant will drop down. But nevertheless, it's the demonstration of how molecular or nano sciences can contribute to our life, and to having a material which has enormous mobility, huge transmission of light, and at the same time being so strong and so flexible. And they are studying different applications, many applications, and and here is an example of a flexible cell phone, which was done by one of the companies, probably LG or Sony or whatever, and the transmissions through such flexible layer. And now I go in the history to the Greek times, to Plato and to Archimedes. And the reason I go to that is that these two giants, two and a half thousand years ago, were already able to observe the difference between structures which are hollow and closed, and they are made of two different elements. Plato was describing the Platonian polyhedra, which are made of the same structures, triangles in this case, or pentagons in this case, and they were able to form a hollow to tessellate the entire surface of a hollow structure continuously without any defect, or if you wish to have point or grain boundary defect, but tessellated completely without leaving any empty space. And 200 years afterwards, Archimedes, which invented the Archimedeans, these are polyhedra which are made of hexagons, for example, hexagons and pentagons, and more precisely 20 hexagons and 12 pentagons, and this is the reminiscent, of course, of a soccer ball, modern soccer ball. So the two fathers of solid-state polyhedra that we call today are Platonian solids, and Archimedean solids are those people. And in the Renaissance period of time, there was a lot of enjoyment using this mathematics or geometry to produce artifacts as ornamental artifacts in churches, in cathedrals, in monasteries, in palaces, of course. And it has been used extensively. And in fact, you can see it in different places in Europe. This beautiful structure. The pioneer was Leonardo da Vinci, and afterwards Kepler, who built this Keplerian. And the Keplerian structures, polyhedra, have for the first time negative Gaussian curvature. So they are not curved only smoothly like that, but they have outgoing structures, surfaces. And this is something, mathematical description, which I won't go into that. But this is the Keplerian. So you see the Archimedeans and the Platonian polyhedra here. And then at the 18th century, the giant Leonhard Euler. Euler and Bernoulli worked together for some time. And as you may know, their main work was done in St. Petersburg. They were invited by Peter the Great to build the Russian Academy of Sciences, and they actually were active there. And Euler, who was a Swiss, and Bernoulli, they were both Swiss scientists. They settled in St. Petersburg for many years, and he did the Euler theorem. The Euler theorem is the theorem that allows us to calculate the structure of this polyhedra and tells us that in order to close a structure made of entirely hexagonal network, we have to have only 12 pentagons. And this is demonstrated by these beautiful domes which were built by Richard Buckminster Fuller. So he, in the 20th century, brought these ideas of Platonian solids and Platonian structures and Archimedean structures into fruition, into architecture. And you know these structures in Montreal and in Epcot in Florida. You see them on the in different places in photographs and in the internet now, obviously. And you know that in order to get this beautiful structure, you need hexagonal network with 12 pentagons, which will lead to this structure. And the question was, can we bring it to the realm of chemistry? Can we bring it to the realm of molecular sciences? And the answer came by the beautiful work of my great friends Smalley, Kroto, and Kell. Unfortunately, Smalley passed away in 2005, and my dear friend Harold Kroto, to whom I dedicate this lecture, died 2 years ago. So they found actually that it can be brought to the realm of nanochemistry or to chemistry, and they synthesized and analyzed for the first time C60, the molecule that is built from 20 hexagons and 12 pentagons. And furthermore, they understood that this unique structure is the stablemost form of carbon when you go to nanostructures. If you now take millions or billions of carbon atoms and divide them so that 60 atoms will be grown or cooked in an oven, each 60 atom in a separate separate pot, they will all form C60, because this is the stablemost structure of carbon in the realm of nanosciences. And this was a revelation, and it started the whole journey of molecular nanotechnology or nanochemistry, if you wish. And not surprisingly, they got the Nobel Prize in 1986. And following their footsteps was Iijima, that in 1991 described for the first time the structure of carbon nanotubes. Now, obviously, he was not the first one to observe carbon nanotubes. The first paper describing carbon nanotubes is due to Raduskevich and Lukonovich in the Journal of Physical Chemistry in Russian in 1952. These are the first picture of carbon nanotubes grown with iron catalyzed. And this is the VLS technique that we are using today to grow carbon nanotubes. But they have not, although they saw these structures, they did not understand that these stable structures are part of our nanotechnology. Namely, they are the most structures of carbon when you go to one-dimensional nanostructures. So this carbon nanotube, you see, by the way, the picture of myself with Iijima a few months ago at the Weizmann Institute. I invited him to give a talk, and in the memory of Millie Dresselhaus. So I'm proud to be close to him, as close to him. I don't know if you know, but Professor Zinnigat described my age factor and my citation. One single paper, the single paper of Iijima is cited 45,000 times, just to give you an example. So it's probably one of the most cited papers in the world. And you see products that are slowly coming into fruition of nanotubes. So these are reinforced polymers that are reinforced with carbon nanotubes. And this is Roger Federer, I believe, with a tennis racket made of carbon nanotube polymer composite. So you see that it slowly comes into fruition. but it takes years of research, huge investment in money in order to be able to control the synthesis. And I just heard 2 weeks ago a beautiful talk on how these single-wall nanotubes can now be not only isolated, but they're with specific chirality. They can be with specific chirality. Chirality is the way you fold over the graphene sheet and make the nanotube. So this is the beautiful demonstration of nanochemistry, nanocarbon chemistry, and it's really a revelation for us. And with that, I will go shortly into my own research in the last 10 minutes. And I will start, again, I'll go back to history. And this is a paper, actually, of Linus Pauling, who received 2 Nobel Prizes. And Linus Pauling was the first person to suggest that you can make nanotubes and fullerenes not from carbon, but from inorganic materials. And he had a model, which I won't go into detail, but he perceived a model describing inorganic nanotubes from chrysotile. Chrysotile is a mineral, is the asbestos basically, and he described a model by which he could think of, or he could suggest. In 1930, there were no electron microscopes at that time, and he could describe already the formation of nanotubes from chrysotile. And at the same paper, he stated that chrysotile will form nanotubes because it's an asymmetric compound. The bases here and the base here, this is the silica tetrahedra and this is the alumina octahedra, are different, and so they are strained and they must fold and form tubes. But a structure like this, which is symmetric along the c-axis, will not form nanotubes. And he mentioned molybdenum disulfide and cadmium chloride and brucite will not form nanotubes. And here came my contribution. So in 1992, just 1 year after Ijima published his work, I came out with the idea that molybdenum disulfide will form nanotubes and fullerenes because it suffers in the nano regime, it forms edges. And the edges are too reactive to remain as a flat structure. So these are 2D materials. The 2D materials are all made of layers, like graphene, made layer by layer. And they all suffer from edge effect. And then when you go to the nano realm of nanoparticles or nano regime, they spontaneously fold and close into closed structures. And if you go and cook them properly, if you learn how to cook them properly, you can get pure phases of these nanotubes and fullerenes from variety of inorganic compounds. And I won't go to the details, but I'll show you just few examples to that effect. And these are the first fullerenes from tungsten disulfide and molybdenum disulfide. You see that they are, unlike C60, they are multi-wall, they have many defects, but they are all hollow closed structures. And these structures are very important because they have many applications. Not only they are a new chemistry, they lead to a new chemistry, but they have new properties which allows them to be useful. And in fact, they are very, very useful. And the first application that we offered was to use them as solid lubricant. As lubricant, we imagined, or I imagined, that these nanoparticles will roll like a nano ball bearing and will form a very, very efficient lubricant. And indeed, this is now an industry, an expanding industry, and it starts now to go through all the world. And we started here in Rehovot, or in Yavne. We started in Rehovot, then we moved to Yavne, and there we built the reactor which can manufacture today 300 kilograms of these nanoparticles per day. And if you think that this is mixed with another, each gram of this nanomaterials is mixed with 100 grams of a lubricant, of any lubricant, which is used in different applications, we are speaking on gross amounts of hundreds of tons today per order. maybe tens of tons or hundreds of tons, and next year it will almost surely will jump to thousands of tons of materials, because the applications are going beyond imagination of these lubricants. And mostly for metal forming, for metal working fluids, for transmission systems in large equipment, for conveyors, for many, many, many applications. So this is an important application, and I just want to, again, to jump back to in history as I used to do. So this is the first demonstration. Actually, this is the oldest picture that I bring to you from the Egyptian period, when they built the pyramids. On one of the pyramids, they found this drawing, beautiful drawing, and you see this person pouring a liquid before the stone, before the sculpture of Pharaoh, and this is the lubricant. So this is the old lubrication of used by the Egyptian. And now we jump to modern times, and we see this paper, which is a few papers now, modern papers, that describe the evolution of nanolubricants, or of lubrication. And in the 21st century, the prediction is that most lubricant will contain nanoparticles. And the pioneer is Reshev Tenes group at the Weizmann Institute. And of course, I cannot forget my great friend and colleague, Lev Rapoport, with whom I collaborated, and I still collaborate, from Holon Institute of Technology, with whom I did the work, and Sidney Cohen, and many, and all my students, which are not described in my scientific work, the discourse. I always give credit to my students, not here. So this is now a large company. This is the factory in Yavne, and it grows now, and it will probably go now to Europe and to Russia and to different sites of the world. So you see the evolution in 1992 to 2013, and you see that every year we went up by more than one order of magnitude in size. And the applications came, and there are now ball bearings, which are made. These are the first demonstration of solid lubricants used in this nanocomposite made of this. And the prediction is that there will be many, many more applications. And just to conclude, I want to show you the nanotubes. These were the first nanotubes that we have described in our paper, and multi-wall tungsten disulfide nanotube. And without going to the chemistry, but since I retired 6 years ago, we came up with a new chemistry, and this is a matter of the scientific talk, which I'll be glad to give. We developed a new chemistry which allows us now to cover most of the periodic table with new nanotubes. We synthesize new nanotubes almost once per month, and with different chemistry, different and new chemistry, which allows us to do nanotubes for more and more complicated chemical compounds. And I won't go to that this time. I don't have the time and the means to do that, not even the power. But just the last few slides are this one, representing the usefulness of this nanotube. So I won't show you the movie, but you see how this nanotube, which is high temperature synthesis, it took us long time to learn how to synthesize it, but now we can synthesize it in kilograms, and it's being synthesized in 3 laboratories in Israel in kilograms. And these are tungsten disulfide and molybdenum disulfide tubes, and you see how beautifully they are. They are strong and flexible at the same time, and therefore they can be used very effectively to reinforce different phases. And we started with different polymers. The first paper was with Lev Rapoport in 2003, where we have shown that we can make very useful solid lubricants based on epoxy and different polymers. And then came many, many more papers, and they are popping up now more and more in the literature. And there is a work that we are also developing here jointly with Professor Zinniger and Dr. Borodoyansky sitting in the audience, which is to reinforce aluminum alloys using these tungsten disulfide tubes. So there is a lot of application, and just the last picture that I want to show you and to give you the demonstration of science and technology, still not nanotechnology in that sense, is that 20 years ago, the most advanced plane was the 777, and it was made of 20% polymer and 80% metal alloys, light metal alloys. Nowadays, the most advanced airplane is the Dreamliner or the 350 of Airbus, and they are made 70% of polymer and 30% of metals. So this gives you the, of course, reinforced polymer reinforced with graphite fibers. This shows the tremendous progress we have done in technology, and the next generation of airplanes presumably will already contain either carbon nanotubes or our nanotubes or boron nitride nanotubes. I'm pretty sure that it's coming. So with that, I would like to conclude my talk, and I hope I gave you some flavor of nanotechnology and the importance of doing basic science in order to advance. Nothing takes one day, nothing takes 1 year. It took me 25 years to get to the position where I can stand and tell you that our products now go around the globe in hundreds and thousands of tons, sold in hundreds and thousands of tons, with predictions of much larger predictions. And it takes usually as much time to go to fruition. So with that, I would like to thank you for your attention, and hopefully you got something from my talk, and I invite you to visit us at the Weizmann Institute.
Thank you very much, Professor Tele. Maybe 1, 2 questions. Yeah. Okay.
Yeah, actually there is now the first screens which are without cadmium, with zinc. Yeah. So it was described also in advanced material last year. Quantum dots for display. I think LG is using them without cadmium, with zinc. And obviously you have tellurium and you have selenium, which are not environmentally very friendly, but nevertheless we have to live with that. And nanotechnology has its negative sides as well. I didn't talk about it, biotoxicity and biocompatibility, but this is things that we have to cope with. Progress always comes with a price, and once you learn how to harness their negative effect, you can use them in variety of applications. So far as you know how to harness this or mitigate the negative effect of nanotechnology. When nanoparticles go to the engine of or transmission system in a car or in a lorry or in shaft, they will eventually also burn out and form some environmental impact or footprint, and you have to come up with technology to recuperate this the oxide nanoparticles and use them for something else.
יש לי שאלה הבאה, אז אנחנו יודעים שבמכניקה קוונטית יש פרדוקסים, שרדינגר קט פרדוקס, wave packet reduction, ובטח שאתם מפתחים את כאלה חומר בכזה גודל, אתם מפגשים את הפרדוקסים האלה. אז כמה זה עוזר לפתור את הפרדוקסים האלה?
Well, I think that we all have to pay an entropy. It takes, of course, I think basically it's not a paradox. It's you know that you have chemistry at nano regime, which is different from the macroscopic regime, and you need more energy or you need more, probably more entropy in order to manufacture nanoparticles. So if you have to take to produce 1 ton or 1 kilogram of this nanoparticle or quantum dots, you probably consume much more entropy or heat than 1 kilogram of cadmium selenide and bulk material. And so this is it's not a paradox, but it's the price of using nanochemistry.
What I'm saying is that one of the most interesting properties of this tungsten inducified is this what is called Valley
Electronics, yes.
Did you look into this in your...
No. The Valleytronics comes into play when you have single layer, graphene like 2D layer. For sure, this is one of the most exciting applications, future applications, but now one of the most interesting physical properties of monolayer of tungsten disulfide or molybdenum disulfide. We are not looking into that. One reason is, of course, that these nanotubes of fullerenes are not coming as single wall. They come as multi-wall, and they don't show this behavior, not at all. They don't even show regular quantum size effect or hardly show quantum size effect. Yeah.
Okay, thank you, Dr. Wong.